Namaste. In this lecture, we turn from the general idea of sustainability to a practical question. How do we measure it? That question is essential because sustainability cannot remain only a slogan or a good intention. We need ways to observe change, compare conditions, and judge whether a system is moving toward long-term balance or away from it. Today, we will focus on metrics, indicators, and boundaries as tools for that work. Our path today is straightforward. We will first define metrics and indicators. Then, we will ask why sustainability needs measurement at all. After that, we will classify major types of indicators, introduce the idea of ecological thresholds, and connect biodiversity to assessment. We will end with some cautions about interpretation, followed by a short recap and a transition to the next lecture. Let us begin by linking this lecture to what we already know. Earlier, we saw that sustainability means development within limits. We also saw that ecosystem services support human well-being and that biodiversity supports ecological function. Once those ideas are accepted, one more step follows naturally. We need assessment. Without assessment, we cannot tell whether our actions are protecting those functions and services or gradually weakening them. Let us start with the term metric. A metric is a measurable quantity. It may be numerical, such as carbon emissions, forest cover, or water quality values. It may also be an organized observational measure. Metrics help us track changes over time, compare places, and detect trends. In sustainability work, metrics are often the building blocks from which broader indicators are created. A metric gives us a measurable piece of evidence. It does not automatically tell the whole story, but it provides an important part of it. An indicator is slightly different. It is a measurable sign of a broader condition. The target image is useful here because an indicator helps us aim at a larger reality that may be too complex to observe directly in one step. For example, dissolved oxygen in a river can indicate an ecosystem condition, and infant mortality can indicate social well-being. Indicators simplify complex realities, help us infer system status, and support monitoring and comparison across places or time periods. So they are very important. Sustainability needs measurement for several reasons. First, we need to monitor change. Second, we often need to compare systems across time or between places. So both on a temporal as well as a spatial scale. Third, planners and policymakers need evidence when making decisions. And fourth, measurement helps prevent vague or symbolic claims from replacing real accountability. Without indicators, almost any project can present itself as sustainable. Sustainability just becomes a word. With indicators, we can ask more serious questions. Are emissions rising or falling? Is biodiversity improving or declining? Is water quality becoming more secure or more fragile? At the same time, it is important to say clearly that measurement does not replace judgment. It's not a replacement. Indicators provide evidence, but they do not automatically tell us what to do. Context matters here. A single number never contains the full social, ecological, or historical reality of the place. Good sustainability assessment combines evidence with interpretation. We use indicators to support better judgment, not to avoid judgment. And this is especially important in biodiversity and sustainability because complex systems can never be reduced perfectly to one number or one chart. Now, because sustainability is multidimensional, its assessment must also be multidimensional. Environmental conditions matter, but so do social conditions and economic conditions. A region might grow economically while becoming ecologically unstable. Another might conserve habitat while excluding local communities from benefits or decision making. This is why sustainability metrics must be integrated rather than narrowly selected. The three-pillar framework from the previous lecture returns here in a practical form. The pillars are not only a conceptual model, but they also shape the structure of our assessments. A useful starting classification is to divide indicators into four broad groups: environmental indicators, social indicators, economic indicators, and composite indicators. Environmental indicators track ecological conditions. Social indicators track human well-being, fairness, and access. Economic indicators assess productivity, efficiency, and long-term viability. Composite indicators combine several measures into a larger index. This classification is useful because it reminds us that sustainability cannot be assessed from one dimension alone. At the same time, we will see that each type of indicator has its strengths and limitations. Environmental indicators tell us about the state of ecological systems and environmental pressures. They may include air quality, water quality, forest cover, biodiversity status, soil health, and carbon emissions. These indicators are especially important because ecological systems form the material foundation on which societies and economies depend. In this course, we must emphasize one point strongly. Biodiversity indicators are not separate from sustainability measurement. They are central to it because ecological stability, resilience, and function depend heavily on biodiversity. Social indicators help us ask whether human well-being is being supported fairly and effectively. These may include public health, access to resources, education, equity, justice, and participation in decision making. Sustainability is not only about protecting ecosystems in abstraction. It is also about whether human communities can live safely, meaningfully, and fairly over time. This is why social indicators matter. A project cannot be called sustainable simply because it preserves a landscape if it also deepens inequality, excludes affected communities, or undermines basic human well-being. Economic indicators assess whether a system is materially viable, productive, and stable over time. These may include income, livelihoods, productivity, resource efficiency, and even the cost of environmental damage. It is important to avoid a narrow view here. Economic sustainability does not mean short-term profit alone. A system that generates income today while undermining soils, forests, water systems, or public health may look successful briefly but fail over time. Good economic assessment therefore includes attention to risk, degradation, and long-term resilience. Composite indicators combine several separate measures into a broader index. This can be useful for communication, ranking, and quick comparison. For example, a composite sustainability score may combine environmental, social, and economic measures. These tools can help decision makers see patterns at a glance. However, there is also a danger. While many measures are combined into one number, complexity can be hidden. Important trade-offs may disappear behind a simple average. Composite indicators, therefore, are useful, but they must always be interpreted with due care. A good indicator should do at least three things. First, it should represent an important reality. Second, it should be measurable. It should be understandable. And third, it should support action and decision making. So these are the three important characteristics of good indicators. And these criteria matter because an indicator can fail in more than one way. It may be easy to count, but ecologically meaningless. So in that case, the first criteria is not being followed. Or it may be scientifically excellent, but too difficult or too expensive to be used regularly. Good indicators balance relevance, practicality, and usefulness. They should illuminate rather than merely produce numbers. Every indicator simplifies reality, and this is a very important point. Every indicator simplifies reality. It's a simplification of the reality. Now, that is both its strength as well as its weakness. Real ecological and social systems are highly complex. Indicators work by selecting one part of the picture and treating it as a meaningful evidence. This can help us manage complexity, but it also means that important details may be hidden. A rise in one indicator does not always mean overall improvement. A stable number may hide deeper instability. And this is why interpretation remains essential. Indicators are tools for thinking, not substitutes for thinking. Some common mistakes appear again and again in sustainability assessment. One is focusing only on what is easy to count rather than what actually matters. Another is ignoring hidden ecological processes such as soil life, connectivity, or resilience. A third mistake is treating one metric as the whole story. And a fourth is forgetting scale and context. A measurement that is useful locally may not explain a regional pattern and vice versa. So we need to be mindful of the scale and context of measurement. Good assessment requires awareness of these limitations from the very beginning. Now let us take a simple example here to illustrate the point. Forest cover is a useful indicator because it can show whether tree cover is increasing or declining over time. But forest cover alone does not reveal full biodiversity quality. A biodiverse forest and a monoculture plantation may both appear as forest cover in a simple dataset. And yet, their ecological value is extremely different. This example teaches an important lesson. Quantity alone is not enough. Good sustainability assessment needs indicators that also speak to quality, structure, function, and diversity. Economic growth provides another useful example. Rising output can be important and it may reflect productive capacity. but growth by itself may hide inequality, ecological damage, or long-term fragility. A region may become richer in aggregate while degrading water systems, exhausting soils, or excluding vulnerable groups from benefits. This means that economic growth is useful as a measure, but it is incomplete as a sustainability indicator. Sustainable development requires us to ask not only how much output is generated, but how it is generated and at what cost. Water quality indicators are particularly valuable because they connect ecology and society directly. Both require water. Water quality reflects environmental condition, but it also matters for health, agriculture, and livelihoods. Changes in water quality can show degradation, restoration, pollution control, or system stress. However, even here, we must be careful. A single water measure should be read alongside others. Water systems are influenced by land use, biodiversity, seasonal variation, and infrastructure. So again, indicators are most powerful only when interpreted in combination rather than in isolation. Now we come to a key argument in this course. Biodiversity indicators matter because biodiversity reflects ecological condition and influences resilience, function, and long-term stability. Biodiversity loss can begin long before dramatic collapse becomes visible. A landscape may look green, a river may still flow, and production may still continue, and yet ecological integrity may already be weakening. This is why sustainability measurement must include biodiversity directly. It's essential. If we leave it out, we risk misunderstanding the real condition of the system. So all other indicators may be going up and still biodiversity indicators may be going down. And in that case, we cannot say that things are sustainable. Students sometimes think of biodiversity as a separate conservation topic, while sustainability assessment is treated as a different policy topic. Now, that separation is extremely misleading. Biodiversity is a part of sustainability assessment because it supports ecosystem services, it shapes the ecological resilience, and it affects long-term human well-being. If biodiversity declines, the reliability of pollination, water regulation, soil function, and habitat processes may decline as well. So biodiversity indicators belong inside mainstream sustainability measurement, not at the margins. Now, biodiversity indicators can take several forms. They may include species richness, that is, how many species are there, trends in species, population status of key species, habitat quality, habitat connectivity, and broader functional or ecosystem level measures. No single biodiversity indicator is sufficient in every case. The right set depends on the question that is being asked. If the concern is habitat fragmentation, connectivity may matter greatly. If the concern is collapse risk, population trends may be critical. And good biodiversity assessment selects indicators that match ecological reality. So we may require different indicators to understand or to explain different parts of the ecological reality. At this point, we also need to distinguish between indicators and boundaries. Indicators tell us about system condition and the direction of change. Boundaries tell us about limits that should not be crossed if system stability is to be maintained. Sustainability is therefore not only about observing trends, it is also about threshold awareness. If an indicator is going down, Are we still at a position where we can recover, or we have crossed the threshold? That is very important to know. We need to know about threshold awareness. A system can appear stable until a boundary is crossed, and after which recovery becomes difficult or costly, or in certain cases even impossible. This makes the idea of ecological boundaries especially important in sustainability thinking. Ecological boundaries are limits within which ecosystems can function safely and support long-term human and non-human life. They help identify levels of pressure that should not be exceeded. If boundaries are crossed, instability can increase, resilience can decline, and recovery may become more difficult. One of the challenging features of boundaries is that damage may not become obvious immediately. This delayed visibility is one reason why sustainability assessment must take limits very seriously before crises become dramatic. Many systems can absorb stress only up to a point, and this creates the impression that small losses do not matter very much. But once a threshold is crossed, change may accelerate rapidly. And in that sense, ecological damage is sometimes non-linear. A wetland can continue to function while under increasing pressure and then suddenly lose buffering capacity. A habitat can lose species gradually and then suffer faster decline in function. This is why early warning matters. Waiting for obvious crisis may mean acting too late. Biodiversity integrity can be understood as one of the central boundary concerns in sustainability. When biodiversity integrity is weakened, system function may also weaken, along with resilience and service reliability. The effects may spread across scales, from local habitats to regional ecological processes. This means sustainability must respect not only visible resource levels, but also the capacity of living systems to maintain structure and function. Biodiversity is both an indicator and a boundary related concern at the same time. Once we accept that sustainability resources are limited, indicators become even more important. They help identify areas of concern, support resource allocation, compare urgency, and improve planning focus. This is true in biodiversity conservation, climate planning, water management, and urban sustainability. The point is not that indicators make choices automatically. Rather, they help us make choices by informing us. In complex systems, decisions cannot be perfect, but they can be made more intelligently when measurement is taken seriously. A strong sustainability assessment integrates ecological, social, and economic indicators and then interprets them in context. This is essential because sustainability problems almost always involve interactions among dimensions. A city may improve economically while heat stress rises and green space declines. A conservation area may succeed ecologically but fail socially if local communities are ignored. Integration does not mean forcing everything into a simple formula. It means reading the indicators together and asking what they reveal about the whole system. Now, scale is one of the most important but often neglected issues in sustainability measurement. A local indicator may suggest improvement while regional pattern shows decline. A short-term gain may conceal long-term instability. This means that both spatial scale and time scale affect interpretation. Good analysis therefore asks a simple but powerful question. At what scale is this indicator being read? Without this question, even valid data can be misunderstood. Sustainability always involves time, place, and system boundaries, as we have seen throughout this course. Now, in this case, baselines also matter. They matter because indicators only become meaningful when compared to some reference point. If the baseline is poorly chosen, decline can be hidden. For example, a system may seem stable if we compare it only to the previous year, while ignoring much larger long-term degradation. So for instance, if a species count has reduced from 10 billion to say 1000, but last year the count was 1001, this year the count is 1000. In that case, we might say that, okay, the species is stable. The values are not changing much. Only 1 out of 1000, that is 0.1% difference. But this is only when we are comparing in 1 year. If we compare it from a value of 100 years back, the change becomes much more dramatic. So baselines measure the changes at different scales, and this becomes very important. Becoming less harmful does not automatically mean becoming sustainable. In many cases, what looks like improvement is only partial damage reduction. So going back to the same example, if last year the count was 1000 and this year it is 1001, we might even be celebrating that yes, the count has increased, while we are not understanding that the count has gone down from millions to thousands. So in many cases, what looks like improvement may only be a partial damage reduction. And historical perspective helps us interpret these indicators more honestly and more usefully. Indicators are only as reliable as the data behind them. That's very important. Weak data can mislead, incomplete data can create uncertainty, and inconsistent monitoring may make trends difficult to interpret. Now, this does not mean we should wait for perfect knowledge before acting, but it does mean that transparency matters. Analysts should be honest about uncertainty, data gaps, and methodological limits. Credibility improves when limitations are acknowledged rather than hidden. In sustainability work especially, trustworthy measurement is often more valuable than overconfident precision. Now, indicators do not operate in a neutral political vacuum. They can improve accountability, but they can also be selected strategically to present a favorable story. The choice of metric shapes what becomes visible and what remains hidden. A report that highlights tree planting but also ignores biodiversity quality tells one kind of story. A report that highlights growth but ignores ecological damage tells a very different story. So students should therefore learn to read indicators critically. Ask what is being measured, what is omitted, and why. Imagine a proposed development project such as an industrial site, a dam, or urban expansion. A sustainability assessment should ask several questions here. What ecological indicators are being used? What social indicators are being used? What economic claims are being made? And are boundaries or thresholds being considered or only the short-term trends? This set of questions helps us move from theory to application. Good sustainability analysis is not about memorizing indicators. It is about learning how to ask better questions of evidence. So, as good sustainability analysts, we should ask four basic questions again and again. What is being measured? What is missing? What limits might be near? And what does biodiversity tell us? These questions are useful because they combine evidence, caution, and ecological awareness. They help prevent only narrow conclusions. They also align closely with the broader purpose of this course, which is to connect biodiversity with real decisions rather than treating it as an isolated academic topic. If we had to reduce this lecture to one sentence, it would be this: sustainability requires evidence, integration, and limit awareness. I repeat, sustainability requires evidence, which is what we are measuring, integration of different evidences, and also awareness of the limits. Evidence matters because claims without measurement are weak. Integration matters because sustainability spans ecological, social, and economic realities. Limit awareness matters because systems can degrade beyond safe operating conditions. And together, these ideas make sustainability assessment more serious, more practical, and more scientifically grounded. Before we finish, let us gather the key terms from today: metric, indicator, composite indicator, ecological boundary, threshold, biodiversity indicator, and baseline. These are the main terms to retain. These concepts will continue to matter throughout the course because later discussions of threats, management, and coexistence all depend on understanding how ecological condition is recognized, interpreted, and monitored. In the next lecture, we shall turn to sustainable development, case studies, and discussions. This next session will carry forward the ideas developed today and deepen our understanding of biodiversity through the lens of ecological relationships and real-world sustainability concerns. Before we close, let us pause for one reflection question. How can the ideas discussed in sustainability metrics, indicators, and boundaries help us understand or solve a real sustainability challenge? Please think about this in relation to local environment, policy choices, livelihoods, or long-term ecological resilience. This kind of reflection helps connect the lecture to practice. And that's all for today. Thank you for your attention. Jai Hind.